Now, the topic is de Broglie's matter waves. Earlier we have seen the particle nature of light radiation, that is, light has a dual nature. It behaves like particle in certain experiment, and it behaves like a wave in certain other experiments. That is the nature of light. This dual nature concept is extended to particles also by one scientist, de Broglie. According to him, nature is symmetric. When light has dual nature, then particle should also have the dual nature. It should also exhibit particle as well as wave nature. He investigated further and found that particles like electrons, neutrons also exhibit wave nature when they are moving with high velocity. These are called matter waves. When a particle is moving with a high velocity, it can be associated with a wave nature, and that waves are known as matter waves. That is a basic concept of matter waves. Matter stands for material particles and wave is a wave nature of the particle. Now, according to him, the wavelength of these matter waves is given by this expression, lambda is equal to h by mv. Here mv is the momentum of the particle, which can be represented by p also. Therefore, lambda becomes h by p. That is the expression for the wavelength of the matter waves. Now, we get this expression using some other simple equations like energy of the photon. The energy of photon is given by h nu or hc by lambda. From that, we can write lambda expression as hc by E. Now, this can also be written as lambda is equal to h by E by c. Now, this E by c is nothing but the momentum of the photon, therefore, this can be written as h by p. So, that is how you get lambda is equal to h by p. Planck's constant divided by the momentum of the particle will give you wavelength of the matter wave. In case of a material particle, generally the momentum is written as mv. Therefore, this lambda becomes h by mv. So, that is the expression for the wavelength of the matter wave. When you look at this expression, that is lambda is equal to h by p, we can understand the basic concept of matter waves. You see, on this side of the equation you have lambda, which is nothing but wavelength. Wavelength is the property of a wave. We represent a wave with its wavelength, amplitude, intensity and so on. Whereas in case of a particle, we use properties like momentum, energy and so on. Here on the other side of the equation you have p, the momentum of the particle. On this side you have wavelength. We are equating the wave nature and particle nature using that expression. That equation itself tells you a lot about the concept of de Broglie's matter waves. Now, on the other hand, for example, if a particle of a bigger size, macroscopic object is moving with a velocity, can we associate that with matter waves? Theoretically speaking, yes, but in practice things are slightly different. We can never detect a wave produced by a macroscopic object, that is large objects. For example, let us consider a body of mass, a ball of mass 0.2 kg. Let us say it is moving with a velocity of 20 meters per second. Can we associate a matter wave with that? We will see what happens. Now, in this particular case, the mass of the body is taken as 0.2 kg and it is moving with a velocity of 20 meters per second. Now, using this one, we will use the wavelength of matter waves, which is given by h by mv. H is Planck's constant, 6.62 10 power minus 34 joule second, divided by mass of the body 0.2 kg and velocity 20 meters per second. Solving this one, you will get approximately 1.6 into 10 power minus 34 meters. That is the wavelength of the matter wave associated with a ball moving with 20 meters per second, and its mass is taken as 0.2 kg. Now, you observe that order of the wavelength 10 power minus 34 meters. It is so small that it can never be detected. Even with highly sophisticated device also, such a wave, such a small wavelength can never be detected. So, we will say that Basically, for macroscopic objects such as the objects which you are able to see with your naked eye, the concept of matter waves is not applicable. Where this matter wave comes into picture is in case of microscopic objects such as electrons and neutrons. Let us say an electron or a neutron is moving with a high velocity, then we can always associate that particular particle with matter waves. We can always determine the wavelength of electron wave also. Remember, electron is basically a particle which has certain mass, whereas we are talking about electron wave, that is the concept of matter wave. When electron or neutron or any microscopic particle moves with a high velocity, it can be associated with a wave nature, that is what we call matter waves. Now consider an electron which is moving with a high velocity. Let us say we have applied a potential difference to an electron and it is accelerated to high velocity. Then in such case you can write an expression for its wavelength also, that is wavelength of the matter wave. Now coming to this expression of the wavelength for matter wave, lambda is equal to h by p, where p stands for momentum. Now let us say that the kinetic energy of the particle is represented by E. This is obviously equal to 1 by 2 mv square. Now I can write this expression as m square v square by 2m. And mv is momentum p, therefore this m square v square can be written as p square, momentum square, divided by 2m. This is equal to energy. That's a relation between energy of a particle, kinetic energy of a particle, and its momentum. From that we can also write this as p square is equal to 2me. From that momentum p can be written as square root of 2me. Now let us say this to be equation number 2 and the expression for the wavelength of matter wave as equation 1. Now suppose if I substitute this 2 in 1, let us say we are substituting equation 2 in 1. In such case the wavelength of matter wave becomes lambda is equal to h by square root of 2me. In that expression, m stands for the mass of the particle under consideration and E is the energy, kinetic energy of the particle. H, as you know, is basically Planck's constant. Now for example, if you are having an electron which is accelerated by a potential difference, then the corresponding energy of the electron can be written as EV. That's the energy of an electron accelerated by a potential difference V. In that expression, E stands for charge of electron and V for the applied potential difference. Now if I substitute the E value in this expression, I will get lambda is equal to h by square root of 2 MeV. Now that gives you the wavelength of electron wave. Now if you look at that expression, except the applied potential V, everything is constant. H, Planck's constant, m, mass of electron, E, charge of electron, and V is the potential difference. Now if you substitute those values and solve it, you will get an expression something like this. That is 1.226 divided by under root of V nanometer. That is the wavelength of electron wave which is accelerated by a potential difference of V. So if you are given, say, an electron is accelerated by 100 volts, then you can simply substitute the applied potential value here and determine the value of electron wavelength of the electron wave. That is the basic idea behind this.